This is a video for OCR Pure Core Mathematics, Complex Numbers 4, de Moivre's Theorem, 4.4, Using de Moivre's Theorem. De Moivre's Theorem can be used to simplify expressions and complex number fractions. Let's have a look at this example. If I look at the top line, I'm going to get 3 to the power 4, that's 81, times the cos of 4 lots of 2 theta, so I'm going to get cos 8 theta plus I sine 8 theta. And on the bottom, I'm going to get 2 to the power 3, that's 8, and then cos of 4 theta times 3, so that's going to be cos of 12 theta plus I sine 12 theta. Now we're doing a division here. If you want to think about this as being a power minus 1 for this bracket, then that would make these angles negative, and so we end up taking away the angles. The moduli just divide. So we get 81 over 8 times the cos of minus 4 theta plus I sine of minus 4 theta. Now just need to tidy up these minus signs. So if we think about cos, helps just to think about the curve. Cos theta is an even function, symmetrical about the axis, so the cos of minus theta is equal to cos theta, and sine theta is an odd function. It has a rotational symmetry rather than a reflexive symmetry, and so the sine of minus theta is equal to minus sine theta. So I can tidy this up over here. I get 81 over 8 times the cos of 4 theta minus I sine of 4 theta. There's that tidied up for you. You can see that this division really does end up with negative angles in here, a negative argument, and there's the bit of theory that we've just been using about cos being even and sine being odd. So we end up with this result. Okay, a second example, and this one is actually again a fraction, but I've written the second power as a power minus 2, and I could put it back into a fraction like I did with the first example, or I can leave it with a negative power, and I'm going to do that for this example just to show you how that works through. And that's going to give me cos of 3 pi by 4 plus I sine 3 pi by 4 and that's going to be times cos of minus 2 pi by 3 plus I sine of minus 2 pi by 3. Well, add the arguments. You're going to get cos of pi by 12 plus I sine pi by 12. 3 pi by 4 is 9 pi by 12. 2 pi by 3 is 8 pi by 12. So we end up with those. And if you plug that into your calculator, you will get 0.966 plus 0.259i. But there is actually a third form of the cos and sine of pi by 12. It's not very commonly used, but you will find it if you look for it, particularly online. So you've got root 6 plus root 2 over 4 plus root 6 minus root 2 over 4i. And these have come from looking at the cos or the sine of pi by 3 minus pi by 4, and then using the addition formulae, actually cos of a minus b and sine of a minus b, using those because we know all about cos and sine of pi by 3 and cos and sine of pi by 4, and you can get them down into this form. Not commonly used, but interesting nevertheless. Okay, so here is all of that worked through. There you can see I've used the negative power to come down to that form and then put it back into x plus iy. And just for completeness, there's the third form for that as well. So De Moivre's theorem, very useful in sorting out powers, positive or negative, of complex numbers expressed in modulus and argument form. The next video in this sequence is 4.5, finding multiple angle identities using De Moivre's theorem.